Well, it's been a while since the last video. I guess we're gonna tear down another power supply. No, wait! We're gonna do something much more exciting. Well, to be fair, we are going to tear down and look at a power supply. It's a very good quality power supply. It's a MEANWELL, open frame 24 volt, 150 watts power supply. But the cool thing about this teardown is that we're going to look at the efficiency of the power supply using a new application that I wrote. But first, let's just take a look at this. As I said, it's a fairly high quality one. And full disclosure, I got this power supply and a whole bunch of other power supplies, including other MEANWELLs and some crappy Chinese ones, from a tweaker called Quindor, who is building a house. And in that house, apparently he is going to install something like 2.5 kilowatts worth of RGB LEDs. Also stuff that he built himself, so his own designed PCBs with like remote control stuff, and it's going to be super awesome. I'm sure he's going to make videos about that as well. But for all of that, he needs power supplies. And he kind of asked me, do you want to take a look at a whole bunch of power supplies and tell me which one is good? Now, first to look at the outside of the power supply. And all these open frame power supplies kind of share a few typical characteristics. First of all, you usually have a perforated steel. In this case, it is galvanized steel on top and stainless steel on the bottom. They usually have screw terminals for the power input and output. This is not something I like, but we'll get back to that later. They are usually not actively cooled, with one or two exceptions in this group, but these are meant to be like, this one doesn't, but a lot of them do have holes on the back that allow for the power supply to be like hung from a wall. Kind of used as like in your distribution box or something to power something. First of all, I thought this was stainless steel, but it's way too light. So this is actually aluminum. So the enclosure is half galvanized steel and half aluminum, which is not too good actually. These two will eventually corrode against each other. Especially in humid environments, so I would have liked to have seen aluminum on both the top and the bottom. Another thing I don't particularly like is that this is never going to come across on camera, but these punch holes are fairly sharp, and I actually see a few burrs on them, so that's definitely not a good thing. On the bottom side, this is a good thing. Instead of a PE sheet, they actually have a very thin piece of FR4. So that's PCB material, and this is much more flame retardant than PE. So the transistors are cooled against the outside, and I think this is 2 millimeters, maybe 1.5 millimeters aluminum. So, okay, this power supply is only 150 watts. And I think it's in excess of 90% efficiency. So the total power dissipation of everything is only about 15 watts. So you can definitely get away with that on this. But in general, this is not a lot of heat sinking, considering like here, this is the primary switch or location of a primary switch. There's a cutouts here, there's a hole here. There's just not a lot of places for the heat to actually dissipate to. Here it's much better on the secondary rectifier. Now to have a look at the PCB. First of all, let me just get this out of the way. I'm probably going to repeat myself in every video, but I really don't like screw terminals. The problem with screw terminals, and especially this arrangement. So here we have the 4 output terminals, 2 positive, 2 negative. And then we have ground, neutral, and live. The issue with putting these all in a row is obviously there could be a wiring error. People are stupid, generally. People are going to make mistakes. And it's just so dangerous to have low voltage wiring, which is galvanically isolated from mains so physically close to mains. Somebody could have like a screwdriver, like if these screws are all the way up, if you have like thick terminals to put in, like these two terminals, they can be close enough that you can poke a screwdriver at it and make contact. Now, obviously they did take a little bit of care. I've seen Chinese manufacturers put the ground next to live. That's horrible. Here they have output negative and ground, which are coupled anyway. So this shorting these actually doesn't have that much of an impact. But they do have these about the same spacing. So this is, yeah, I just don't like this. Also, I don't like screw terminals because they don't have positive retention. It's just these screw terminals, they can get loose. A lot of people don't use the right connection, so you really have to use a blade connector that has been crimped. A lot of people use solder connections or bare wires, which is the worst because copper work hardens. So if you wiggle a copper wire that's just directly wired into this, the copper wire will eventually break. All the little strands will start to break, and it's just horrible. So don't use screw terminals, but it's kind of standard for open frame power supply, so I can't really fault them for that. Now, after that whole ordeal, if we look at the input filter, I'm not too happy actually. Again, this is a good quality power supply. Generally speaking, MEANWELL makes okay stuff, but in this case they have a fuse, and they have a CLC, and then the diode bridge, and then they have some inrush current limiting resistors. They do have coupling, so they have a proper differential and common mode filter. I'm not sure exactly what this is, but this is probably some kind of flyback, or maybe it's a CD filter. And they have a ground coupling capacitor, but there are clearly places for, this is a, they call it a Zener, probably like an MOV or TVS type device. They have better coupling capacitors. They have footprints for a full power input protection, but they don't have any MOV or overvoltage protection. So not too happy with that. Also, this this diode bridge it's just unsupported. There's not even goop around it, and it's almost against this MKP capacitor. This will get warm, not too hot, but it will get warm, so it will reduce the life of this cap. And also it will increase the resistance of this PTC, or I guess NTC, inrush current limiting resistor, so kind of diminishing the effects of that. Also, this is pretty standard with these power supplies. This is an input voltage selector. It's nice that they even have this. Usually they just come in one voltage type because they don't have PFC. And this is standard. Like I've said this on one of the earlier videos, like I think the first 24 volt open frame power supply, I thought something was PFC, but it was actually just a driver circuit. There's essentially never PFC in open frame power supplies. And it's weird. And well, I guess they can get away with it. These apparently don't fall under consumer electronics, and consumer electronics and instrumentation and even some industrial stuff is required by the European Union to have PFC if they draw over 75 volt amps. Well, they're not required to have PFC, but they are required to have a power factor over 0.8. For which you need active PFC. Also, I am very sorry to inform you that these are Lelon caps, which are kind of a B grade manufacturer. Lelon is better than the Zhangji or other shitty capacitor manufacturers. It's still, again, these are the primary caps. They are 105C rated, so it is okay. The primary caps don't really have that much current going through them, so it doesn't really matter. They don't really get hot. So it's all kind of fine as long as these are good quality, and they are. So they have pinched pennies where they can. Like also the PCB material is kind of crappy. Seems phenolic. But yeah, they did invest where they have to. Anyway, there's the input or the primary switch, which is just a MOSFET. Yeah, GDS, which is driven by. Well, I thought I was just going to cut there and tell you exactly what this chip is, but it's branded MEANWELL. It's an MW03A. So apparently they have rebranded some other chip. This is obviously a flyback controller because there's only one primary transistor. There's clearly some current sensing, so it's a current mode transistor. And there is a snubber, and that's it. So, yeah, whatever. I don't know why they rebranded themselves. Maybe they got a good deal. They obviously, MEANWELL is one of the largest power supply manufacturers in general, so they can afford to have that. They probably make millions of those chips. Kind of interesting to see they have two feedback optocouplers. Yeah. That's weird. There's definitely two different ones. That is very intriguing. Why would they need two? Well, anyway, I won't really dwell on that too much. Also, extremely interesting to see. So that's just a transformer, nothing to see there. It is a properly shielded transformer, which is very nice. This will not kick out a lot of EMI. Now, this is the coolest because they have, like, there's GDS here. So this means these have to be transistors, right? Wrong. They laid it out in such a way that they can insert these jumpers. And if they do that, they can install a diode. So this is a diode. This is not an active rectification. It's really cool. They can, like, I think on the higher power versions, they just install more capacitors and they install these two transistors instead of diodes. And they install, because that's the other way to see this, they apparently then install a chip here, which does the active rectification control. It's not installed here, like there's nothing on the backside. There's just like the voltage divider here, which is also tunable, and then there's a resistor for the LED. And then the only real filtering they have is an LC, so they have a CLC, which probably is enough. Before I forget, was just looking at this, seeing if I forgot anything. Isolation slots everywhere, like here and here and here. There's even some on the capacitors there. This is a safe power supply. This will not explode on you. This will get all the safety ratings, and I'm sure EMI ratings are good as well. So as far as that goes, pretty good. Alright, so here is the setup we're going to use for the efficiency measurement. First of all, in the past I did a noise measurement, and I did that using the oscilloscope, and this wire going into channel 1, which is terminated in 50 ohms. Unfortunately, I found out after a couple of comments that it's not actually a matched impedance network, so it will not give me accurate results. So I'm not going to do noise measurements right now. That may come back later, but right now those measurements will be meaningless anyway. So what you see here is, this is the new box. It is an AC power meter, my own design. Very happy with how that worked out. It goes into the power supply, obviously, via this wire, and out of the power supply, this is the setup, the load tester setup that you've seen before. Little current measurement board, voltage measurement, and then there is a whole bunch of resistors which are cooled by fans, and all of that is controlled by this little PCB that turns on and off those resistors and measures back the current and voltage. All right, so here is the efficiency setup that I made. And right now you're basically just seeing way too small text and a couple of bars, I guess. I have the AC power meter and I have the DC load, and those are connected to two different USB ports. And what I'm doing here is I am connecting to both of these boards through to this one page using this program, which is a serial to WebSocket proxy and some, well, actually a lot of JavaScript. I am dividing the input or the output on the input power to calculate the efficiency and correlating that to the output power. So on the horizontal axis, we have the output power, and on the vertical axis, we have the efficiency. And what you can see here, right on the bottom left, this is some data points that are slowly being collected. These data points, you can see every data point is an individual measurement. And for instance, if I increase the power, so now we see data points appearing here. Actually, this data point is an outlier. So here we see this little cluster of data points forming. And these are all valid measurements. So these are measurements of the AC input power and the output power. And what you can see, which is very interesting, is that actually these points are not all the same. They have quite a lot of spread. This horizontal line and this horizontal line between here is 5% efficiency difference. So the lowest point here is 77.5% and the highest point is 79.5%. There's quite a lot of spread. And this is the most awesome thing, I think, of this entire exercise. This spread is normally distributed. So you can see that right in the middle here are many different measurements are in this like 78.5%-ish range, and then very few measurements are on the outskirts. So what you can do with this, that's the most fun I've had all day, is you can transform this into a mean value and a standard deviation. So again, I'm sorry about the tiny text. I will export this image to my website and link it in the description so you can look at it in detail. But what you can see here, or maybe cannot see here, is that there's a tiny little cross, and the cross denotes the standard deviation and the mean value of this efficiency here. So what I can do is I can now add more measurements. So now I make a measurement at about 3 watts. Actually, there's another outlier here. I can delete outliers, which are usually caused by glitches. Go back to the cluster view, and I can make another measurement point at about 1 watt. Again, get rid of the outlier. And now slowly you can see this efficiency curve emerging. So now we're measuring at 11 watts output. It's about 84% efficient. And now as we build up this efficiency curve, so more measurements will mean you get a better estimation of the actual efficiency. And this is also something with my company makes measurement equipment, precision measurement equipment. And what you often see on the internet is these perfect curves. So for instance, a review site tries to measure, I don't think they really measure efficiency, but they try to measure like output voltage and voltage drop and that kind of stuff. And they have these 5 significant digits and say, well, the output voltage started at 24.451 volts and then ended up at 23.886 volts. Those kinds of numbers, they seem very accurate, but they're not. They are without some kind of measure of how accurate they actually are. So without doing repeated measurements of the same kind of data point and seeing exactly how those data points are distributed, whether it's a proper normal curve or if there's some skew in your measurements. Without that kind of information, you have no way to ascertain how accurate it actually is. And the same goes for this. So I will always try to hammer home this concept of please show your standard deviation, show your mean value. And for instance, here I can see on this last data point at about 11 watts, 10.95 watts, with a standard deviation of 16.7 milliwatts, we can see that the standard deviation of the efficiency is 0.4%. So it is 83.94% is the mean, but there's actually quite a lot of inaccuracy in the AC power measurement. So this is helpful. Then you can see how well you can trust this data and whether you can really say that, for instance, if you compare this to an 83.8% efficient, so 0.15% less efficient power supply, you can say, well, yeah, it is, the mean is slightly lower, but it is still well within the standard deviation. So you cannot really say it is definitely less efficient. Anyway, I will go on and build this efficiency graph. We can get a general gist of how this power supply performs. Well, we see kind of good efficiency, but you have to keep in mind this is a 24 volt power supply. High voltage means that your main cause of inefficiency in a power supply, which is the secondary rectifier, is actually more efficient. That diode, the efficiency of the secondary rectification is almost entirely caused by the voltage drop of the diode. And if you have a higher voltage and the same voltage drop on that diode, you get higher efficiency. So generally, you expect 24 volt power supplies and also 19 volt power supplies to break 90% efficiency. And what we see here is that all the way from, well, let's say 80 watts up to max power, it is just flat at just over 89% efficient. It is, though, very nice to note that although this is a 150 watt power supply, and at 150 watt it is 89% efficient, it still has very decent efficiency at 15 watts, or actually this is 16 watts. It's still 86% efficient at 10% load. That is very good. Usually you see them drop down to below 70, especially lower voltage power supplies. And even at very low load, at 3 watts output, it is still 75% efficient. So quite happy with that, actually. And of course, it's also interesting to see what the output voltage does and how well it performs when you load it down. So let's just load it up. Yes, 149 watts. And the output voltage is still 24.12 volts, so it has excellent output regulation. Also, it doesn't seem to have any real noise on the output. I would see it if there was a significant amount of noise. Now, what we're also going to do is see how much power we can actually draw from it. So what's its actual maximum rating, if it goes into overcurrent protection at any point, and how it handles overcurrent. So we're now at 170 watts. The output is still 24.11 volts, so it's still regulating very well. 175 watts, 180, 85, and we're done. So basically, yeah, now it goes into hiccup mode. So let me just reduce power. Yeah, it does go to 185 watts. So it has overcurrent protection about 20% over its volts. Oh, and now it does have significant noise on the output. It has a lot of ripple. So you can kind of load it up to 185 watts, but not really. Yeah, the output current is sagging a bit. So, but yeah, 20% margin on the power supply, which is just very good. So yeah, what can we really say about this power supply? It's a good little power supply. 150 watts is not a lot for a 24 volt power supply, and it clearly has a lot more headroom. It has proper OCP. It's very simple inside. Has meh input capacitors, but those are not that important. Very good output capacitors. Generally good quality. Fairly thoughtful. Couple of less than ideal things like the relatively bad deburring on the aluminum part of the enclosure. Yeah, what can I say? It's a decent power supply. I wouldn't have any trouble deploying this in your house, and will probably run for like 20 years with the kind of components and big spacing, especially if you don't load it down continuously at like overpower or anything. So as always with these things, it's hard to give this a one number reading or that kind of stuff. I'm not that kind of guy. I just like to go in depth, show you every aspect of it, and then you can say for yourself what you think. Anyway, this video was mostly just to show off the efficiency graph stuff, which I just think is really cool. And hopefully you've enjoyed it as well. In the next review, I will also try to do noise measurements and include the thermograph again, but yeah, this time the video is already taking very long, so I decided not to include those.